Thank you, everyone. Yeah. I'm Sander van der Boer. You probably know me better as the guy behind California's team, the LED light up wearables. Oh, a little bit closer. Okay, there you go. So today I'm going to talk a little bit about my previous designs before I even start doing supercapacitors, what I learned during that process. And then we're going to dive into the supercapacitors, show you what's available out there, and do some calculations with those. So my wife and I, we started California's team back in 2017. We were doing workshops in the community, and we were getting grants from the Stockton Arts Commission. And in order to get those grants, we needed a business and a business license. So we came up with California's team, where we added art to STEM to make it STEAM. The main focus back then was still doing workshops. I was sewing. I had my sewing machines out there, and we were putting LEDs within wearables to light them up. But then in 2018, my wife was so nice to get me a table at like a festival. I just had to come up with the product. Yeah, that's all. Yeah, a little challenge. So since I had all the equipment already to make my own PCBs, I decided to make an light up wearable, like an earring. I did horrible at it. The show was for Day of the Dead. I sold maybe one pair. Took me 2 months to get ready and then selling one pair. But after putting these on ATtiny, people were starting to get interest, and that's what motivated me to make more designs. So my first design were these spiral earrings. They were powered by a cone cell battery, the CR1225. You get about 52 milliamp hours out of those. They were controlled by an ATtiny 84A. That was back then the smallest ATtiny you could get. It's a 3 by 3 millimeter footprint. So I designed it. I used actually white LEDs because I thought if you use white LEDs, the forward voltage is actually higher than 3 volts. So the cone cell battery cannot do any harm. I didn't know that the cone cell battery would never do any harm because it's not able to apply enough current. But back then that was my thinking. So I designed it. I was running it with the Arduino, just pulsating the LEDs, and I was able to run it for 4 hours. That was it, and it died. I didn't do anything to harvest the energy, not using any sleep modes, nothing like that, and it just died after 4 hours. But after optimizing it, I was able to get 30 hours out of a single battery. So yeah, the code was done in Arduino, and I'm just flashing the LED. So it's ATtiny 84A. They have like 12 pins you can control, and I was controlling 12 LEDs, so it's really simple. You just pulsate each pin. The same order of variances I did back then was the skull, shamrock, and an art palette. The only one I have on here today is the skull. I still have the little spirals on here, but today I'm using the ATtiny 1616 for those spirals. And I'm doing a little bit different way of controlling those. I'm actually using PWM today to make them look more smooth. Because back then, the pulsating it, if you would film it with your camera, it would look horrible. So now with PWM, it actually looks good on the camera as well. It increased, I wrote down some numbers here. So originally, I was only using 52 microamps. And in the redesign, it actually increased to 300 microamps. But yeah, it looks better. Also, kind of a funny fact is, after I learned that you can do any LED on there, right? You're not limited to just white. So I put red on there. It actually increased the power consumption to 1 milliamps. So with the red LEDs, my power consumption went up 3 times. So after that, I learned more about the ATtiny's 1 series. I was working on another project where I needed additional timers. And on the 84A, you only have like, I think, 2 timers, and I needed at least 3. So the 1 series came out, and I started using that on my other projects. I was running servos and NeoPixels at the same time, so I needed additional timers. But I started also using those on my wearables. I went to the ATtiny 412 because actually it's a bigger footprint, so I was able to solder these by hand. I was kind of tired using the stencil because I always had to rework them. So I was making it easier on myself just to resolder that thing entirely by hand. And I also was experimenting with reverse-mounted LEDs. So what you can see here, these rocket ships, the flames are reverse-mounted, and they're pointing to the board to make it look like a flame. I also started using Atmel Studio and programming these directly, using code in Atmel Studio. And in this case, I was using the real-time counter of the ATtiny to do the PWM. So I'm not really using the timers that are designed for the PWM. I was using the real-time counter because that way I was able to keep it in sleep mode much longer. Order variances on those were the sun and moon and the teddy bear. And then during COVID, I decided to take on a bigger project, and that was the Fibonacci earrings. So I wanted to do, I was always interested in doing a sunflower. And while I was doing the design, so the project started as a sunflower, but while I was doing this design, I learned more about Fibonacci and how those sequence numbers are actually determining the spirals you can see in a sunflower. Also, I thought I needed a lot of power, so I went to cone cell batteries for this design, and I used two to get to 2.8, 2.9 volts to actually power the LEDs. And I had to go to an ATtiny 1617 to have enough pins available to control this matrix. So for the matrix, I was using an 8 by 13 matrix. They're both Fibonacci numbers to control 104 LEDs total. It was during COVID, so I had plenty of time to work on this project. Just, sitting at home. It took me a couple months to figure it all out, and after I was able to get this all running, they were running for 30 days. I was planning to have these running for at least 10 hours, and it was 30 days. So I was off with some of my, well, I would not say calculations because I didn't do any calculations. Also for this, I used the TCB timer, which is a timer that can pulse. So what it does basically, I tell the timer how to stay on for a certain time. It will just pulse and turn on one LED, goes to the next, does the same thing. So it does it 104 times to control each individual LED. So I can actually change the brightness if I have to. Some order variances I did was, another thing that was kind of what happened here was JLC PCB was offering pick and place. So I was not going to do this by hand anymore, which allowed me to do 104 LEDs because it was going to be crazy to do this all by hand. Also, these were 0402 LEDs, so they were all just super tiny. It was just impossible. Order variances on these were the Tree of Life, those were RGBs. And a golden ratio, and you can see these all on here, so maybe later you can go and take a look here. I have the Tree of Life and the golden ratios on here. And for those I used even smaller cone cell batteries because, well, you have enough power in those anyway. The Fibonacci earrings actually allowed me to, well, they were a big success, so I had a little bit of income. That allowed me to make two big purchases. One was a label printer, because that allowed me, it saved me so much time on shipping. And another one was I got one of those NRF power profiler kits. And when I hooked that one up, I learned that my power consumption was about a little bit less than 1 milliamps when it was like 2.8 volts. And it dropped way below 1 milliamp when it was at 2.7, 2.6 volts. That's why it was running so long. So this was going great. And then Rishi's law, kind of came in place. So suddenly Etsy deactivated all my listings. I got an email first that said, hey, we deactivated one of your listings. And I go there and everything was just gone. They deactivated all of those. And it was because cone cell batteries can be deadly if they're swallowed by kids. That's why they don't longer allow this kind of products on their website. So look for alternatives like LiPo batteries, but those are dangerous too. They could explode or you have shipping restrictions, so I was not really happy with the alternative. I was already doing some experimenting with supercapacitors, Here you see an electric double layer capacitor, an EDLC. They're purely electrostatic. These are great because you just charge them up to a certain voltage, and you don't have to worry about it. You can just, and they discharge, and then you charge them up again, no harm. The only problem is you have a low energy density. So like in this case, what I used here on this little, I call the duck, it's a 5.5 volt because there actually are two capacitors in here, layered on top of each other. 5 farad capacitor. So you don't have a lot of capacity here, but simply you just charge it to 5 volts. There's no charging circuit required. And you can just run them entirely empty without doing any damage. They have a very high power density. So if you need something that needs a bright light or you want to flash something, these are great. You're just only able to flash it 10 times and then your capacitor is empty. With every capacitor, you have a linear voltage drop. So you're starting off with 5 volt and then it slowly goes down to 0. So if you're powering your LEDs, over time they get dim. But they're very safe. It's very difficult to break these, or I haven't tried putting too much voltage on these. I'm not sure what will happen if you put 10 volts on these, but I think they have a vent, so they should just vent out. These were just too big for my wearables because I have to calculate how much it actually is, but it's only a couple milliamp hours you can get out of this capacitor. And my goal is always to run the wearables for at least 10 hours. So this would not allow me to actually run the earrings or anything else that I was going to design from this capacitor. Besides that, you need a charging circuit around it, like a USB connector. There was just no space on the PCB to do that. So I kind of gave up for maybe a week. And then I was on DigiKey again, and I found some very interesting 20 farad capacitors that were much smaller. And those were lithium-ion capacitors, LICs. They also call them like a hybrid because it's kind of in between a capacitor and a battery. So they're electrostatic on the cathode and then electrochemical on the anode because they use a little bit of the lithium ion. The minimum energy density it's much higher than a regular capacitor. So that allowed me to start using these. I'm showing the picture here. These are actually 4.2 volt capacitors, and they're basically the same capacitor. One is 90 farads, another one you can see they label it like a battery with 50 milliamp hours, which is plenty. If I stay around 1 milliamps, I can run these wearables for 50 hours of a single capacitor. They have a high power density, so if you still want to pulsate some LEDs with it, it's great. But you're still going to have a linear voltage drop, which hasn't been really an issue to me. I've just allowed the LEDs to get dimmer over time. There's just one problem with these capacitors, or actually a couple problems. First of all, they're only rated for 3.8 volts or 4.2 volts, so you have to limit your voltage if you're charging these with your USB power supply. That's 5 volts. And then you cannot discharge them too far. So there's an under voltage of 2.5 volts on most of them. And if you go below that, you could harm the capacitor. So you have to somehow build in your circuit a way of turn off your power supply from the capacitor to your device. But the big advantage is the fast charging and a very long cycle life. So you can charge them up to 100,000 cycles if needed. And someone actually wrote an article about my first wearable and said that's enough for the next 2,000 years. But USB-C is probably obsolete by then. So they're also safe. They're exempt from dangerous goods controls per the 66th edition of the IATA dangerous goods regulations. So there's no shipping restrictions as long as you stay below 300 milliwatt hour, which is quite a big capacitor if you go there. So here are the most common LICs I've found. So I started off with 3.8 volt capacitors, Teardown. This was the one I found on DigiKey. I got a couple. I just hooked it up to one of my Fibonacci earrings just to see if it worked. And, well, it worked. Back then, I had no under voltage protection, so I was just measuring the voltage with a voltmeter, and that's when it got too low, I just pulled it out, and I had no way to charge these. So I could do this test once, like, okay, this is going to work, but then I was stuck. Then I ordered some CDA from AliExpress. Those are the LIC series. They also have a 2.5 volt minimum. Actually interesting that the Kari, according to their data sheet, they can go down to 2.2 volts. But usually I just cut it off at 2.8 volts. So yeah, you have the CDA you can get from AliExpress, and then I found a supplier on Alibaba. There's the KNSCHA, and they call them burst cap, which is kind of a funny name for a supercapacitor. Yeah. So they have the N series, and those also have a 2.5 volt minimum, and that's what I've been using on my wearables most of the time. Then Wyman, that's kind of a new supplier. You can get those from let me see, LCSC. I'm not sure if I'm saying that right. Yeah, LCSC. Then CDA also makes 4-volt capacitors. They call the LIB series. And I'm not sure if the B stands for battery, and the other one, the LIC, is for capacitor. But they almost doubled the capacity, and those are rated for 4 volts. But on my latest series, I've been using the one from the burst cap series again, the H series. I call it the purple version, which has 2.5 times the capacity of the N series. So I was talking to them last year, and I told them I need just a little bit more capacity. You have a bigger capacitor. And they come up with a purple version that you cannot find anywhere that had 2.5 times more capacity. So it's great. I've been using it on my latest wearables, and yeah, they just last 2.5 times longer. So my first LAC-powered supercapacitor earrings were using the 3.8 volt 20 farad capacitor. So it's about 7.5 milliamp hour. Back then, I didn't know how to charge these because I was thinking about using a regular LiPo IC, but those are always rated for 4.2 volt max. So I was afraid that I would damage the capacitor. So I was using a Darlington transistor for constant current, and then a Zener diode for overvoltage protection. So when it was getting close to 3.8 volt, it would just slowly drop the power going into the capacitor. Besides that, I also used the MCU. So the MCU was measuring, the chip itself was measuring the voltage going into it, and was also able to turn off the charging circuit if needed. So that way I knew I was always staying at 3.8 volts, but if the chip was not working, it would still cut it off with the Zener diode. For the under voltage protection, I just used the sleep mode on the MCU. 2 minutes? Okay, I'll try to go quick. And then my power consumption on this one was between 0.3 and 0.7 milliamp hours. Runtime was 10 to 30 hours on this design. Charging you can do in 3 minutes. Then next was the redesign of the Fibonacci earrings. 3.8 volt, a 40 farad capacitor, got 15 milliamp hours out of those. Same concept, same design of circuit. And you get 10 to 20 hours out of those, depending on the LEDs used. And then my Amarazzi earrings, there I used the 90 farad capacitor. They claim it's 50 milliamp hours. According to my calculations, it's a little bit less. And there I started using a regular LiPo charging IC. I prefer the TP4102, but it has like charging current limits, over and under voltage protection, short circuit protection, and indicators for the charging and the done indicators. Runtime on this one is up to 30 hours, because these are pretty big. Charging is a little bit longer, because I'm using that TP4102 IC. The charging is about 6 minutes. Okay, so to go from the to calculate your capacity in a capacitor, you can use this calculation. So you know your capacitance in farads, which is per voltage. So On the left, you see my equations. On the right, you see an example where I take the Vmax, like the 3.8 volt minus 2.5, so you get 1.3 volts. You do that times the 40 farads, you get 52 coulombs. That's your charge that your capacitor can hold at that moment. And it's very easy to go from coulombs back to, it's actually 1 amp second. So to go back, you go 52C divided by 3.6, you get your milliamp hours. So for 40 farads, I get 14.4 milliamp hours. Here are some more examples. For the 15 farad, I get 5.5 milliamp hours. And here's the example with the 90 farad. I get 42.5 milliamp hours. So a little bit less than the spec sheet was claiming. Also experimenting with overcharging a 3.8 volt LAC. I've been overcharging them for the last 6 months. I've been doing that for 7,000 cycles. And I've not seen any issues. So after doing that for 7,000 cycles, I lost only 10% of the capacity. Then for my low power consumption, I'm using an NRF profiler kit. It's a must if you want to do this kind of products. I use PWM to control the LEDs, which eliminates the use of a current resistor. You don't need it. I use kind of a hybrid PWM because I'm using the sleep mode too. I update all the LEDs and I go back into a sleep mode to conserve energy as much as I can. And we're running kind of short of time, so maybe I can go to the specs next sheet to show how I'm doing that. So here is the results from the NRF kit. My average power consumption here is 1.6 milliamps. The gray area is my sleep time between updating every LEDs, which is only 500 nanoamps. When I'm updating the LEDs for 700 microseconds, it's about 9 milliamps. But by keeping that sleep mode so long, I get to really low power consumption, in this case of 1.6. Okay, recap. LEC offers a compelling, safer alternative for batteries, but efficiency is key. So you have to make them really power efficient before you can do that. And in the future, I'm trying to use more colors. I have an example here I'm working on right now. And maybe use something more like sensors. Thank you. I can take questions outside if...